Right, hiya guys. I'm going to go through a few questions from, to do with discrete random variables, primarily the binomial distribution, but as you'll see, the questions that I've picked are discrete random variables in general. Now, I'm starting with number 6 here. Right, now number 6, it asks you to construct a table given the probability distribution of t. Now, I'm telling you, well, not telling you but I want you to see that t is definitely a binomial distribution anyway. Why? Because we've got a constant probability of success, that's 1/4. They're all independent, obviously. There are a fixed number of trials, there's 4 trials, and you know, it's binomial, so t is binomial with parameters 4 and 1/4. Right, now, if I was to construct that table then, you know, it'll look like this, the way all discrete random variables, probability distributions look. So probability, I've called it x. Well, now I'm going to say t equals x, weird. Funny that. I'm just going to work these out, but let me do it the way I've mentioned this before, using this function on your calculator. If I go to menu and then 7, I want binomial PD because I want the individual probabilities that it equals each of these. So that's why it'll be PD. So there's that. Now, I'm going to use this list function because I can put 0, 1, 2, 3, 4 down here. 0, 1, 2, 3, 4. And then I'll work out, well, the calculator will work out the probabilities for the other column. When I tell it that n is 4 and the p is 0.25. And now it'll populate it with the values that I want. So I'm going to have to write little, but 0.3164, 0.4218, 0.2109, 0.0468. Yeah, I'm happy with this with 4 decimal places. And then that, 0.0039. 0.0039. So that's the probabilities from that particular binomial distribution. And then find the probability that t is less than 3. That's these, isn't it? 0, 1 and 2. If I add them together, what do I get? When I have 0 and 1 and 2. So I moaned about this, or I have moaned about this before. T is less than 3. There's no other way to do this apart from to get your normal calculator out as it normally is and just add them together. 0.3164 plus 0.4218. I'm going to say something now actually important. Plus 109. What's that? No. Equals, there you go, 0.9491. That's the probability that t is less than 3. What does that mean? That means that, what's the probability that on this particular dice, that I roll fewer than 3 6s out of these 4. Now, I just want to say, look at these numbers. I should have said this before, but look at these numbers. I'm going to say the mode. What's the mode? The mode is what you would anticipate it to be. It's the one that happens the most. So the most likely is 1. So, you know, just think about that from the language and method GCSE. So the mode here, it is what you would expect to happen, which is 1, really, and that's something, you know, nice for me to say. Right, okay, let's look at this next part. It's a different situation. This time we're going to roll the dice 5 times, or a maximum of 5 times, and S, the random variable S, is the number of times I roll the dice until I get a 6. So I might roll it once if I get a 6 on my first go. I might roll it twice, which would mean getting not a 6 and then getting a 6, and so on. So the possibilities for S are, and it'd be little s that I'll write here, I can roll the dice once, twice, 3, 4, or 5 times. And then I'm going to record here the probability that S equals S. Don't really love, stay to that. Don't really love S as a variable because are you on to, that's a big S and that's a little s. That's the name of the random variable. That's the specific instance of the random variable. But what does this mean? S equals 1. So what does the probability that S equals 1 mean? It means I roll the dice once. In other words, I get a 6 on my first go. So the probability of that is going to be a quarter. So I think I'm going to write it as a decimal, 0.25. Okay. Right. Now, what does it mean when S equals 2? That means I get a non-6 on my first go. So the probability that's 3/4. And then a 6 on my second go. So a quarter. So that is, like, times them together, 3/16. That's 0.1875, isn't it? Okay. Right. And I carry on like that. So what's probability S equals 3? It's 3/4 on the first 2 times a quarter. It's 2 non-6s and then a 6. Okay, so if I work that out, I'll do it properly on my calculator. 3/4 squared, oh, you can't see that, sorry. 3/4 squared times 1/4, there we go, 0.14. I'm going to write 1406. I'm going to stick to that convention, 0.1406. And then probability S equals 4 is, so it's 3 non-6s and then 1 6. So 3/4 cubed times, delete that, put a 3 there, times a quarter, and there we go, 0.1055. So 0.1055. And now I'm going to stop because just understand what I mean by S equals 5. S equals 5 means the dice gets rolled 5 times. So it doesn't mean I get a 6 on my fifth go. It means you roll the dice 5 times. And he says in the question he'll stop once he gets, well, after his fifth one. So this is just all those added together and then take it away from 1. So add them all together. I'm conscious of rounding them, but I don't mind. Like, that's the game I'm playing. Like, I've rounded to 4 decimal places. So 0.25 plus 0.1875 plus 0.1406 plus 0.1055. And that is 0.6836. So 0.3164. That's what my answer is there. Okay, 1 minus that, so they all add up to 1. And that's it. And then the question asks on what's the probability S is greater than 2. So weird. Is that not working? Yeah. Probability S is greater than 2 is 3, 4 and 5 added together. Or 1 minus these two, whichever. Okay, so however you work that out, 0.5625. Okay, that's them 3 added together. That's what that is. Right, so that was question 6. Right, I'm going to talk quickly about question 8. Well, I'm not going to talk quickly about it, just it is a quick question. Right, so number 8. The coin is biased, so the probability of a head is 2/3. It's tossed repeatedly. What's the probability the first tail will occur on the 6th toss? So just like what we've just done then, you want to have 5 heads. So 2/3, 2/3 to the power 5. And then a tail on the 6th toss, so times 1/3. And when you work that out, you get, well, let's just write it. Like, I'm just going to do it as a fraction. So 2 to the power 5 is 32. And then 3 to the power 5 times 3, so 729. And just leave, well, you can leave that as that or put it as a decimal. It doesn't matter, but I'm just going to leave it as that. Okay, right, now, B. In the first 8 tosses, there will be exactly 2 tails. Well, I'm going to define my variable now. So I'm going to say, let X, we're talking about tails, so let X be the number of tails. So X is the number of tails. Okay. In the first 8 tosses, there will be exactly 2 tails. So X is binomial. There's 8 tosses, Here we go. And probability of a tail is 1/3. And what do I want? I want exactly 2, it says. So x equals 2. So I'm going to use, because it's equals, I'm going to use binomial PD. So 7 binomial PD. It's just a variable that I want. So x is 2. N is 8. And the probability is 1/3. Where is it? There it is. Okay, equals, yeah, nice one. 0.2731. 2731. So there's me probability there. Okay, right. Next question I want to look at is, well, do you know what? It's question 10. Okay. Right, now, I'm not going to write down the answer to A, but I do think it's very important that you be able to say what the conditions are under which it's appropriate to assume a binomial distribution. And that is, first and foremost, independence. So the trials need to be independent of each other. Secondly, the trials need to have, either need to be success or failure. Then you need to have a fixed number of trials and a fixed probability of success or failure. So that's what you need. They're the conditions. And let's just have a look at the situation in number 10. So this door-to-door salesman, is it binomial? Well, yeah, you've got a fixed probability of success. It says it's 0.05. You assume it's independent. You assume the houses aren't talking to each other. The other thing is there are 10 houses, so that's our fixed number of trials. And then either the salesman's either successful or not. So it satisfies the criteria for it to be binomial. So let's do this then. So I need to define my variable. So let x be, what's x? The number of successes. So x is the number. I'm conscious of writing a bit weird here because I'm hampered. So sorry about that. The number of successes. It is disgusting though, like, sorry. So x is binomial with parameters. There's 10 houses and the probability of success is 0.05 in each one. And we want, let's interpret this language. We want at least 2 successes. We want the probability that x is at least 2. Greater than or equal to 2 is what that means. So x is greater than or equal to 2. And now I'm going to draw a little picture. I'm going to draw it over here so I've got room to represent that. So here's my binomial distribution with all the houses he's knocking at, all the different probabilities or possibilities for success. 0, 1, 2, 3, 4, 5 and some other numbers. I want to have greater than or equal to 2 successes. So I want all of them to the right of 2. So I'm including 2, at least 2 and onwards. Therefore, I'm going to have, that is 1 minus x is less than or equal to 1. So probability x is less than or equal to 1. Either use the table or use your calculator. I feel like I've used my calculator loads, although this is binomial CD. But I'm going to use the table here. It's 10 and 0.05. I'm only using it because 0.05 is in the first column. But there we go. So it's 1 minus that number there, 0.9139. So that's what it is. So I'm going to write that. 1 take away 0.9139, which is 0.861. That's my answer. Right, okay. Now, this is why I picked this question, is for C. I like C, me. So I want to know the smallest number of houses he must canvass so that the probability of his getting at least 1 success exceeds 0.99. So many words in that question, you know. What am I talking about here? I'm talking about now a binomial distribution where I'm trying to work out how many houses I've knocked at. So it's ended in trying to find, still maintain this probability of 0.05. And now I'm trying to work out so that the probability that x is greater than or equal to 1. I'm going to write And I'm gonna do this knowing full well that what I'm writing is wrong. I'm gonna write equals 0.99 there. And I don't really mean equals 0.99. I mean is greater than or equal to 0.99. But do you know what? There's enough greater than and less than knocking round. I just want to have equals there. Just to clarify me thinking. But I know in my mind I want to go actually bigger than 0.99. But let me put that for now. And then I'll sort it out later. Right, now, what does this mean, guys? This is so important. X being at least 1, so at least 1 success. I'm going to draw a bar chart. So I don't know how many bars I've got. We'll never draw them all anyway, do we? 0, 1, 2, 3, and so on. Okay, so there's what we've got. Now, at least 1 success is, and I still remember learning this when I was in like year 12. At least 1 success means all of them. It means 1 minus x equals 0. So I've got, and this is why it makes it easier. So that is 1 minus probability x equals 0. Or less than or equal to 0, but equals 0 in this case. Equals 0. That was a funny 99. Okay, so let me just rearrange this. I'm trying to find probability x equals 0 equals 0.01. Now, how do I get x equals 0? I'm going to do 0.95 to the power n. Think about that if you can't get that, guys. That's really important. X equals 0 means no successes. So every single one is a failure. Equals 0.01. And I'm going to stop now. And I'm going to say, at this point now, what in the maths we've done, we don't know how to solve equations like that. We can't solve equations like that. So what we do is we just use trial and error. So if I go to my normal calculator and I just try some values for n until it gets to like 0.01. So I'm going to do 0.95 to the power, I don't know, 50. Well, 50 is not big enough. So 0.95 to the power 70. Still not big enough. I want this to go to 0.01 or lower. So we'll try something else. 0.95 to the power 100. Too big. Okay, and eventually, and I know the answer here, like, so it's maybe a bit quicker. 89 is slightly too big. 90 is just the right size. So I'm going to write them two down, and that's how I get my answer. So it's a bit annoying while we don't know the technique that we would use to actually get this ourselves, but it doesn't matter. 0.95 to the power 90 is 0.009, and 0.95 to the power 89, or I should have just pressed up, is 0.0104104. So that's the one that we want. So what's that saying? It needs to knock at 90 houses, and well, I used to do that for a job, you know, and that's the sort of thing they used to say to us. They used to say, oh yeah, knocking 100 houses. Right, that's all I'm going to say. Those are some examples of different types of discrete random variables questions, and they're all quite tough. So have a look at what we've just done there. Well done, guys. Nice one.